Cosmology is the scientific study of the universe's origin, structure, evolution, and ultimate fate. It explores fundamental questions about space, time, and matter, including how the universe began, Big Bang theory, how it is expanding, and what its future holds. Cosmologists study cosmic background radiation, dark matter, dark energy, and large-scale cosmic structures to understand the universe's laws and composition. It combines physics, astronomy, and mathematics to uncover the mysteries of the cosmos. The universe is unimaginably vast. I know that sounds cliché, but the scale really is incredible. Right now you are living, breathing, sentience, born out of a dead rock, flying around a single star in a galaxy containing some 400 billion others, 400 billion stars, each with their own planets and stories. The Milky Way is brimming with so many stars that we could never possibly explore every single one, and yet the Milky Way is microscopic and indistinguishable when compared with the rest of the universe, even just our local region of the universe, in fact. But why is the universe like this? Why is the cosmic scale so large and incomprehensible? And of course, the biggest question of them all, how large actually is it? The observable universe is estimated to be around 93 billion light-years in diameter. Contained within its expanse is thought to be as many as 2 trillion galaxies. Assuming these galaxies are similar to the ones we observe around us today, then there may be up to 1 septillion stars in the known universe, and yet they make up only a tiny percentage of the universe's unprecedented scale, which could be hundreds, thousands, or even millions of times more volume in us. This is our universe's story. The first thing to consider is language. What do we mean when we say the universe? The universe is defined as all of space and time. All points in space, at all points in its life. Space is the volume within the universe, the three-dimensional field which lies beyond Earth's atmosphere, acting as the vast backdrop to the universe's matter. Time is the constant flow of cause to effect within this space, the catalyst of life, death, creation, and evolution. Space and time are fundamentally linked, and they combine to form a system of nearly unknowable complexity known as space-time, which is often referred to as four-dimensional. In this model, space constitutes 3 dimensions, and time is the 4th dimension, and any 3D cube cross-section along this axis represents the universe. At a certain point in its life, our understanding of space, time, and a great many other scientific ideas can be traced back to this man, Albert Einstein. He understood space and time in a way that nobody had done prior, giving us 2 fundamental frameworks with which we model our reality today. In 1905, Einstein presented his theory of special relativity, changing the way we view light, mass, and energy. Then in 1915, he presented his theory of general relativity, a comprehensive interpretation of gravity, space, time, and their links. These elegant theories have survived in science for more than a century, and they underpin a lot of what we know about the universe. Today, according to Einstein, mass is a form of condensed energy, which has a warping effect on the flat plane of space and time that lines our universe. The resulting curvature on this flat plane is felt as gravity. Gravity is the effect of objects of mass attracting one another by distorting space-time. It is the simplest yet most profound of the fundamental forces which govern our universe. We don't need anything special like heat. All we need is mass. If you have mass, you have gravity, and as such, it dominates the behavior of the universe at all levels. From the small particle level interactions to the large-scale behavior of galaxies, our understanding of the latter owes to this man, Edwin Hubble, an American astronomer who is not afraid to take on the biggest questions, making a number of groundbreaking discoveries. Before Hubble, it was believed that the universe was static, in that it was neither expanding nor contracting and was populated entirely by stars and nebula in every direction. However, in late 1924, Hubble found that one such so-called nebula was actually a separate collection of stars like the Milky Way, but much further beyond than originally thought, leading to the revelation that the Milky Way galaxy is in fact part of a larger universe of thousands or perhaps even millions of other galaxies by the end of the decade in 1929. Hubble then followed this up with one of the greatest discoveries of all time, that the universe itself is expanding and not static. These revelations, along with Einstein's theories and the work of some other great scientists, have all fed into our current model of cosmology, the lambda cold dark matter model, or lambda CDM. This is a well-established and documented model for cosmology. Admittedly not without its shortcomings and unanswered questions, but it is still our best effort at comprehending the origins and nature of the universe nonetheless. So far, that is central to it all is the Big Bang theory, the idea that the universe began as a point of extremely high density and pressure, because we know that our universe is constantly expanding. If you trace this ongoing process back to the beginning of the universe, you come to a point where the universe was microscopic and compressed before it suddenly began to expand. We're not sure how or why, but there is good evidence that at the very least, the universe was much smaller and hotter. Around 13.8 billion years ago, the time proceeding crosses into the untestable realms of physics, but we believe that in the earliest nanoseconds of the universe's life, something caused it to suddenly and radically expand, in an event known as cosmic inflation, bypassing the benchmarks of all known speeds and laws, changing the universe not in size but in scale. The tiny universe as it was in that moment was enlarged, scaled up by a factor of at least 10 to the power of 78 in volume. Every nanometer of space was stretched to over 10 light years, and all of this happened in under a fraction of a second. We're not sure what the total expanse of the universe was after this inflationary epoch, but what it meant was that the universe's interior was suddenly spread apart, much more sparsely, giving its primordial energy a lot more room for things to happen after inflation. As the temperature of the universe continued to fall, the energy within condensed into a giant universal plasma, and from there decayed into the first particles and then into subatomic particles like protons and neutrons. Fast forward almost 14 billion years and the universe is now huge and brimming with much larger and richer structures. Atoms have collected into clouds of gas, and gas clouds have become stars, and today most of those stars belong to enormous ancient galaxies. Most of these galaxies are gathered in large clusters and superclusters, which all connect to form a 3D path across intergalactic space known as the cosmic web. When we talk about space, most of the time we are referring to the observable universe or the known universe. This is a spherical geocentric region of space that is comprised of all the galaxies and matter that can be detected from Earth, because their light emissions have had enough time to reach the solar system since they were emitted. Light travels at just under 300,000 kilometers per second. That is extremely fast, the fastest speed attainable in the universe in fact. But even just beyond our galaxy, there is a light delay which impairs our ability to see the universe as it appears now. That's why it helps to use light years as a unit of measurement. Proximus Auri, our nearest star, is 4.2 light years away, meaning we see the star as it was about 4 years ago, and that's just on a stellar scale. The space between galaxies is incomparably larger. The distance between us and our nearest spiral galaxy Andromeda is around 2.5 million light years, so we see Andromeda as it was when humanity had only just started using stones as tools. The further away a galaxy is, the longer the light travel time and the younger the galaxy appears to be, and so the deeper we look, the further back we are looking in time through the different stages of the universe's life, and nothing has allowed us to look deeper into this rich history than the magnificent Hubble Space Telescope. The Hubble telescope is a bus-sized satellite which launched in 1990. It orbits the Earth and faces out towards space, allowing it to image the universe undeterred by atmospheric disturbances which hamper ground-based telescopes. It has a number of different instruments and filters and has received numerous upgrades throughout the years, which have kept it at the forefront of human technology. Hubble has snapped over 1.1 million bedazzling images of the cosmos since its launch from nearby stars and nebula to galaxies at the very distant edge of the observable universe. Its deep camera technology allows us to look ever deeper into space, revealing a much younger universe that has been constantly changing and evolving. Nothing captures this evolution quite like the Hubble Deep Field. The Hubble Deep Field image is one of the most important images ever. It was taken in 1995 after Hubble received a servicing upgrade 2 years earlier, which dramatically broadened the telescope's ability to see the most distant galaxies. Around 1/10 of the Hubble telescope's operational time is allocated to high-ranking staff and physicists wishing to study unexpected phenomena. And so the then director of the Space Telescope Science Institute, Robert Williams, devoted his time slot to imaging extremely faint and distant galaxies as a means to test our theories on the age and size of the universe. Unlike most of the images captured by Hubble, which usually have luminous target, the deep field image was created by focusing the telescope's instruments on a tiny, seemingly empty patch of the night sky where nothing can be seen from the Earth. In order for this to work, the telescope needed an area with a high enough galactic latitude that the field would not be obscured by the light from the Milky Way's core. Thus, a small area was chosen in the constellation of Ursa Major, also known as the Big Dipper or the Plough. The point chosen by Williams was tiny. An area roughly 1/12 of the diameter of the Moon in the sky, equivalent to a mere 1/24 millionth of the total night sky expanse. Over some 10 days, the telescope gathered light from the area and 342 photographs were taken using a variety of the telescope's filters. The data was then processed and the image was compiled, revealing a majestic view of the universe's history. Contained within this tiny pin-sized segment of the sky are over 3,000 galaxies at an array of distances, including some of the oldest and most distant that had been discovered at the time. This image isn't so much a representation of distance in the universe, rather it is a window back through time. In the shallower field, we can see rich spiral galaxies, but the further back we travel, the less luminous and structured the galaxies become. Most of the very distant galaxies in the image occupy only a few pixels and shine much less brightly because these early galaxies had not had much time for vigorous star formation, but instead had lots of early star-forming gases. The presence of many unstructured irregular galaxies in the early universe reaffirms our belief that after the Big Bang matter began building from the ground up, first atoms, then stars, then clusters of stars, then Tauric dwarf galaxies, and after billions of years of star and death and countless galactic collisions, rich spiral galaxies like the ones we see here, began to form compound galaxies bursting with luminous stars. If we were able to see the most distant recesses of the deep field as it is today, then we would probably see large spiral and elliptical galaxies like we do in our surrounding space, but again, light just gives us that special opportunity to step backwards through time. In the following year, a follow-up deep field image was taken to ensure that the original was truly representative of the distant universe. The results of the Hubble Deep Field South image were much the same this time, even capturing the light from a quasar in the early universe. After another servicing mission to Hubble in 2002, the telescope was able to take even deeper images still, and in 2004, they snapped the Hubble Ultra Deep Field, the deepest photograph of the universe ever taken from the constellation of 4X. This image reaches the limit of what is possible to observe through visible light in space. To see any further back, we need to use infrared radiation, a 2009 servicing mission to Hubble equipped it with new sensitive infrared detecting instruments, and Hubble snapped all 3 deep fields in infrared, this time revealing thousands more primordial galaxies and several of the most distant ever to be observed, and we probably won't get a better picture than this one, until the James Webb Telescope finally launches. Edwin Hubble and his accompanying legacy have had a profound impact on modern-day astronomy, but of his discoveries, one sticks out from the rest, underpinning everything that we observe and have spoken about today: cosmic expansion, the discovery that the universe itself is expanding. This came about after Hubble had surveyed 24 newly discovered nearby galaxies and had established a linear relationship between the radial velocity of the galaxies and their distance from Earth. Simply put, galaxies outside of our local galactic group all appear to be moving away from us, and the further away they are, the faster they appear to be receding. Everything in the universe seems to be moving away from everything else into its own pocket of space without changing its position. Hubble's conclusion was that space itself is expanding at a consistent rate, all points spreading the galaxies of the universe further apart from each other. When space expands, new space is created everywhere, all over the universe. Space itself stretches apart in every direction to make more space. It is like the universe is inflating rather than expanding, because all objects are getting further away from all other objects relative to each other. There is no center space, has no boundaries, edges, or walls that mark the end. So how do we go about visualizing this? Well, imagine that the sphere represents the universe, but rather than space being on the inside, it is mapped to the outside surface. As the sphere expands, the surface area of the space for the outside galaxies increases at the same rate, and as such, there is no center. No galaxy on this sphere's surface is any more central than any other galaxy. Of course, the spirit itself does have a center, but this doesn't represent a physical location within the universe. Rather, it represents a point in time, the Big Bang. It's an odd concept, but what this means is that even if space is finite and only occupies a certain volume, you could still roam around the universe indefinitely without meeting an edge. Much like if you were to fly an aeroplane round the Earth's equator, you would never fall off or run out of Earth to fly across. Instead, gravity would just bring you back around to the same place eventually. So if you were able to travel considerably faster than light speed in a straight line, you would still come back to the same place eventually. We can see evidence of the universe's expansion everywhere thanks to a phenomenon known as redshift. Redshift is when electromagnetic radiation such as visible light undergoes an increase in wavelength. The wave is stretched out, resulting in a decrease in wave frequency and photon energy for visible light. When analyzing a galaxy's spectral emissions, this has the effect of shifting the absorption lines of certain elements towards the red end of the spectrum, turning visible light red because the universe is expanding at all places at once. As the light emitted from other galaxies travels towards Earth, the space it travels through elongates, stretching out the waves and red shifting the light. The more distant the galaxy, the further across ever-expanding space the light has to travel, and so light for more distant objects is redshift more, and we can use this to determine how much the universe has expanded since said light was emitted. The Hubble constant, a measure for the rate at which space is expanding, is thought to be around 65 kilometers per second. Per megaparsec, a megaparsec is equivalent to about 3.2 million light-years, so the more megaparsec there are between us and a galaxy, the more space there is between the two that is expanding, causing the galaxy to recede away faster. For example, 100 megaparsecs away, the space is receding away from us at a rate of over 6,500 kilometers per second because light speed is limited to about 300,000 kilometers per second. There eventually comes a distance from the Earth at which galaxies are being pushed away from us faster than light speed, not by breaking any laws of physics because they themselves are not moving that fast, but because there is simply too much space between us and them for their light to be able to cross the universe in time to reach us. This constitutes the edge of our observable universe, the boundary beyond which we are unable to see any further. The cosmic horizon or the particle horizon before this boundary, light from distant galaxies has had enough time to cross the expanding universe and meet our telescopes. But beyond the cosmic horizon, the light from the galaxies has either not had enough time to reach the solar system, or it is so far away that it will never be able to reach the solar system. As time passes older and more distant, light has time to pass through the solar system and the observable universe grows, increasing our field of view. But this is entirely dependent on our position. For an observer at the cosmic horizon, space would appear much the same but relative to us. The space beyond the horizon is what's known as causally disconnected, unreachable, and undetectable to us by any known means because our observable universe is geocentric. The same is true of any planet in the universe. Every pointed space has its own arbitrary, observable universe with a radius of about 46 billion light-years marked by a cosmic horizon. This radius is determined not by how far away the most distant objects we have seen were when their light was emitted, but rather how far those objects are estimated to be now, as the space between us and them has grown so much since that light began traveling towards Earth. The most distant galaxies of the Hubble ultra-deep field have now receded to in excess of 40 billion light-years away from the Earth, and their light would never possibly have enough time to reach us. Now beyond the cosmic horizon, light speed and the university's age are no longer compatible, and thus we are confined to our observable universe, segmented and detached from the full scale of the cosmos. Because of this, we are unable to conclude on what could lie beyond the boundary, but given that the universe appears to be relatively isotropic on a large scale, you would expect more of the same clusters and superclusters of galaxies. The real question is how much of it is there as you might expect. That is a very difficult question to answer, and the estimates we have so far depend on measurements of the universe's curvature and assumptions about its shape, which still represents a somewhat gray area in cosmology. I'm skipping over some very complicated maths and science here, but in short, the best estimate we have so far made by physicists at Oxford University is that the total area of the universe must be at least 250 times the radius of the observable universe. This puts the total diameter of the universe at over 23 trillion light-years, which would mean that the 93 billion year observable universe that we can see accounts for a mere 1/15 of its total expanse. If our observable universe is home to 2 trillion galaxies, then the unobservable universe may house as many as 30 quintillion of them. In truth, we will probably never know the exact size of the total universe, but with the numbers considered here, it seems almost inevitable that somewhere else in space life must be playing out on another world. The discovery of the universe's expansion is one of the most important discoveries ever, but we still didn't have the full picture for a long time afterwards. Astronomers expected that the rate of expansion would actually start slowing down as the galaxies on the inside begin to pull back against the universe's inflation. However, as scientists quest to establish a more accurate value for the Hubble constant, a startling discovery was made. Since Hubble redshift, surveying techniques have improved significantly, and we can now detect galaxies not just millions of light-years away, but billions, because redshift is indicative of the universe's expansion. We can compare a galaxy's distance with its redshift to determine how much the universe has expanded at the different stages of its evolution. But that's easier said than done, because galaxies vary in brightness so much so it becomes very difficult to estimate their distance precisely. A more suitable means to measure cosmic would be to take something with a known absolute magnitude known as a standard candle and calculate its distance by analyzing the dimness of the object relative to how luminous it should be. With this in mind, two separate projects, the High-Z Supernova Search Team and the Supernova Cosmology Project, both attempted to measure the expansion of the universe over time by using distant Type 1a supernova as standard candles. Type 1, a supernova as superluminous explosions caused by white dwarf stars in binary systems. They have a relatively consistent brightness and can outshine their entire galaxy using these stellar ghosts as calling cards. The two projects measured the distances of far-out objects and then compared this with each object's respective redshift values. The unlikely result was that the very distant objects seemed to be much further away than the more local objects. It's as if the universe has expanded more in the latter half of its life, or rather its expansion is accelerating. We know that our universe has been expanding at different rates based on what it has been through in its life, and at one point it did look to be slowing down as it was once predicted to do so, but then around 4 billion years ago, and for a completely unknown reason, an invisible force began to hijack the universe's growth, causing its expansion to accelerate, leading to more aggressive expansion. In its recent few billion years moving into the 21st century, we had opened the path to a new paradigm of astrophysics. The study of dark energy. Dark energy is the term given to the invisible force that is responsible for the accelerating expansion of the universe. We know barely anything about it save for that it appears to work like an anti-gravity force. It exerts a negative repulsive pressure that behaves inversely to gravity, which is aiding the universe's expansion rather than slowing it down. Dark energy is notoriously hard to study. It does not interact with light, so it cannot be seen nor detected, and there are many hypotheses describing its nature and prevalence. But what we do know is that around 9.8 billion years of cosmic time, this energy became the prevailing energy in the universe, marking the beginning of the dark energy-dominated era. In the early universe, radiation dominated its behavior. Then for almost 10 billion years, matter was the dominating influence. However, as the universe has expanded, the density of matter has been falling as it has been spread more sparsely. Dark energy, on the other hand, is believed to remain consistent in its density, meaning more of it pops into existence proportionally as the universe expands. Thus, there came a tipping point around 4 billion years ago where the density of matter fell below that of dark energy, preventing gravity from slowing down the universe's expansion, and instead began speeding it up, casting the oldest, most distant galaxies much further away on a local scale. The expansion of the universe is very weak, and so gravity is able to keep objects such as galaxies held together regardless of how big the universe becomes. However, the massive cosmic void between galaxies and galaxy clusters are growing from within their dark interiors, gradually separating galaxies and galactic groups like our local group into their own isolated pockets of space. But because the expansion of the universe is accelerating thanks to dark energy in time, space will be growing so quickly that even our nearest galaxies will receive away from us much too quickly for their lights to ever be able to keep up. Gradually, galaxies at the edge of the observable universe will start disappearing from view as their light is no longer able to keep reaching the solar system, and the cosmic horizon will begin to draw inwards. This will continue until even our nearest galaxies are flung beyond the cosmic horizon, rendering even our local universe invisible. In the very distant future, every galaxy's view of the universe will start and end with its own stars, with nothing but empty darkness. Beyond the outer rims, we will never see another galaxy again. With galaxies separated from one another, they will not be able to merge and will thus eventually stop producing new stars. The Milky Way and Andromeda galaxies will merge before any of this happens, but after that, the resulting elliptical galaxy will gradually burn through the last of its stars. Inevitably, the day will come when the last stars of the universe have either gone out or exploded, bringing the universe into a second eternal dark age. Ultimately, the universe's energy will be lost through natural processes until nothing is ever able to happen again. The universe will reach its heat, death, the ceasing of all heat and energy exchanges. Thereafter, the universe will be a totally homogeneous, incomprehensibly large and boundless void, eternally dominated by dark energy. A bit of a depressing ending to be sure, but there you have it. The fate of the universe in the age of darkness. If you need any other topic and idea concept, so please comment me and like, share and subscribe my channel for other video. Thanks from Relax Audiobooks.